All right, welcome back. So today we're going to work up to stating this black hole information paradox. And I'm just going to do a quick review of what we covered last time. And then I'm going to lay out some of the things that we still need to establish in order to even state the problem. So we're not going to state the information paradox precisely until the end of class. Okay, but that's the goal of today, which is to state the problem. And then next week's lecture, which is the last lecture, we're gonna talk about some more modern developments regarding ideas of how to resolve the problem. Okay, so a review of what you covered last time. Well, last time what we studied was we studied Minkowski space, but in Rindler slices. So we considered a family of geodesics. The family of geodesics described constantly accelerating observers, and we decided to write down the metric of Minkowski space in terms of this family of geodesics. And the metric looked something like this. It was and this covered these coordinates covered one wedge. Minkowski space could be the right or the left wedge, but it only covers one. And we studied quantum field theory in these coordinates. So this is nothing more than Minkowski space, but viewed as a uniformly accelerating observer. So if you're at constant xc, for example, then you are uniformly accelerating. And we discovered that by studying quantum field theory for this observer would measure a thermally populated state. So that was the statement that we have the Minkowski vacuum. So we work in the vacuum of flat space. But this is not the same as the Rindler vacuum. And in particular, this Minkowski vacuum had the property that if I computed, say, the expectation value of the number operator in the right wedge, then I got Boltzmann distribution. Which told us that this is a thermally populated state of bosons where the temperature, T, was B over 2 pi. Everybody can see if I write here?
Just a question. This is what happened with non-respect acceleration. Would it also be a Boltzmann distribution, or would like just everything breaks down?
No, you can study that problem. It's not as easy. I mean, you probably might observe a time-dependent temperature. It really depends on how adiabatic your acceleration changes with time. Without more details, I can't tell you more. Okay, so the last thing that we covered last time was to connect these coordinates with the coordinates of the Euclidean black hole. So the thing that we ended on was the statement that this acceleration it acts the same as this identification of Euclidean time for the Euclidean black hole, and therefore this toy calculation mimics exactly what you would do if you were an observer who is standing at some finite distance outside of a black hole. You would also measure a temperature, and the temperature would be the local acceleration that you need in order to stay at a finite distance from the black hole. Okay? So, so this established that not only is a uniformly accelerating observer in flat space, do they observe a thermal population of particles, but so does a person standing outside of a black hole. Okay? So that this kind of calculation is the origin of the fact that black holes radiate. Is that clear? Okay. So now we're going to introduce what is special about these states. What is special about this Minkowski state such that you observe a thermal populated spectrum? So the important thing to notice is that so I'm going to write down a few more formulas that we derived last class. If you don't immediately recognize them, I invite you to go and watch the video. Okay? So last class we wrote down that the Minkowski vacuum is one that is annihilated by all the annihilation operators for all p, which meant that we could relate that to the creation annihilation operators in the Minkowski slices. So you guys remember we derived this relation last time? Okay, so this relation, and this is for all momentum S. S is now the Rindler momentum, and sorry, and that equals 0. So the state is annihilated by this combination, rather than just a simple single creation operator in the other coordinates. So what does this tell us? So this is an interesting combination. This is an interesting combination because you can show that this implies that you can write the Minkowski vacuum in terms of the Rindler vacuum. Remember the Rindler vacuum, so just to bring it full circle, the Rindler vacuum, what I call OR, is such that B, S, L, or R on this thing equals 0. So that's the definition of the Rindler vacuum. It's exactly the same as how we define the Minkowski vacuum, but we have to use the Rindler annihilation operator. So this combination, it might not be obvious to you if this is the first time you see such a combination, but if you stare at it long enough, you'll observe that you can write this Minkowski vacuum as some constant times the exponential of the integral over S e to the pi s over b times b s L dagger b s R dagger acting on the Rindler vacuum. This is a very non-obvious formula, but you can show that it's true, and I leave this as an exercise to you when you go home. But you can show that this is true So to show that, can everybody read this expression? I know it's not like BSR dagger, and then this is a closed parenthesis. So that's all inside of the exponent, and then acting on the Rindler vacuum. Okay. Okay, so you can show that this is true just by using this. So what you want to check is, given this, that acting with these combinations of B's and B daggers kills this state, right? Because that's the definition of the Minkowski vacuum. And you can just check by acting on this state and using this relation and the Baker-Campbell-Hausdorff formula. So you guys remember what that is? So if you have an operator x and an operator y, then that's equal to the nested commutators. So the claim is using the Baker-Campbell-Hausdorff formula, and this, you can show that this combination and this combination annihilates the Minkowski vacuum, if you write it like this. Are there any questions about that? Like, I understand it's not very obvious what a state like this means, and I'm going to explain it. So I just want you to see that the Minkowski vacuum, if you trust me for a moment, the Minkowski vacuum can be obtained by a certain operation starting with the Rindler vacuum. Okay? I can act with a particular operator on the Rindler vacuum. The Rindler vacuum is the state annihilated by the Rindler annihilation operators. And by acting with this very complicated operator, I can construct the Minkowski state. Okay? You have to sum over all the momenta. It has to be true for every S, this statement, for all S. Any other question? Okay. So the statement that, and this will be true also. So whenever I work in the Rindler problem, I want you to think that an analogous statement can be made about the black hole problem. Okay. So the Rindler vacuum acted with all these creation operators gives the Minkowski vacuum. So you can kind of see that I act with an exponential number of creation operators to get the Minkowski vacuum. Obviously, from the point of view of somebody who's a Rindler observer, this thing will be a very populated state, right? This is very far from the vacuum. I've acted with an exponential number of creation operators, right? Okay, so let's study this state a little bit more. So I'm writing my Minkowski state as so I'm going to drop the normalization constant. These are all in the exponent.
What was the B
parameter? B is the constant acceleration, the acceleration of the observer. In my notes, it's A, but then there was also A's, like there's A's and B's. I'm keeping the same notation as in last lecture, where I called that B. My notes are going to be posted online. In my notes, it's called A. So it's just B is the acceleration. So in that family of curves, B was the acceleration of somebody at xi equals 0. Xi equals infinity had no acceleration. It's a static observer. Okay, so acting on the Rindler vacuum, and then let's start to expand this out. Let's think about what this means. So remember, when you act with like a creation operator on the state, you create a mode of a certain momentum, right? Okay, so what does this tell us? And this is a left creation operator and a right creation operator. So what does this tell us? So you can roughly write this as a product over energies omega and a sum, so I'm going to call this omega I, and a sum over the number, because when you exponentiate something, you're going to get the thing, then the thing squared, and the thing cubed, right? Okay, so you get from 0 to infinity, e to the minus pi n I omega I over b. So you get 0 particles on the left and right, 1 particle on the left and right, 2 particles, and each one has this Boltzmann factor over here, and then you have to integrate over all momentum. This product over momentum is like if I took this integral out, and e to the sum is the product of e's, and then this sum over numbers is just because the exponential of a number operator will give you 1 particle state, 2 particle state, 3 particle states, so on and so forth. Okay, so why did I write it in this form? I wrote it in this form because in this form, it looks like a very particular state that you may have seen in quantum mechanics. And that state is called an entangled state. You guys remember what an entangled state is? We're going to review that, but it's important to see that just given this construction, studying this problem, this Rindler problem, all we remember, this is very simple stuff. We started with free quantum field theory in Minkowski space, and we decided to study it in these particular coordinates. And the observer in these particular coordinates observed a thermal state. And then just going through the motions, trying to understand what this means that for this observer, their state is a highly entangled state between the right wedge of Rindler, which I'm going to draw again. So remember, states are on complete Cauchy slices, and what we're observing is something that is maybe not super surprising, but that the vacuum of Minkowski is highly entangled between the left and the right. Highly entangled state between the left and the right. And according to a Rindler observer who only has access to one side, they're observing this entangled state. Right. Thermally populated entangled state. But we're writing the vacuum. This is the Minkowski vacuum. So according to a person who only has access to one side, they're highly entangled with the stuff on the other side. And that entanglement is a crucial feature in terms of phrasing the information paradox, right? Because your state outside is highly correlated with the state inside of the black hole. Okay? So I'm gonna go and explain. I'm gonna do a digression on entanglement.
Sorry, just understanding the analogy, the right side of the black hole and the left side of the black hole render the outside of the black hole. The right side and the left side.
Yeah, if you have an eternal black hole, like you could imagine, this is the right Kruskal wedge and the left Kruskal wedge. Real world black holes don't have that, so you can think about it as the inside and the outside. Yeah, the inside of a black hole is, yeah, it's the part that, so black holes that are formed from collapse, the Penrose diagram looks like this. There's like some shell, there's a horizon, and a complete Cauchy slice uh, it can look like anything. Okay, it can go inside, it can even end outside of the black hole. We'll talk about that later on in the. It's very important to keep track of all of this stuff in order to properly formulate the problem. So it's good that you're asking this question, but it'll become clearer later. Okay. So I'm aware that not everybody is an expert on entanglement, so I'm gonna review that stuff now. Is that cool? But as you can see, what we have derived is a very simple statement that when you restrict to one wedge, you're gonna observe a highly entangled state. And that highly entangled state just tells you again that the vacuum is one that's written on a complete slice, and you've only got access to one part, and therefore, you know, this thermal behavior is encoding the amount of entanglement that you have in the vacuum. Okay? Sounds a little bit surprising, but you've now derived it. Are there any questions? Excellent.
So like you, the kind of thermal behavior at one point needs the geometry of the whole spacetime, but like mechanism, like it doesn't let you transmit information after like you in like, but the behavior here is kind of the whole spacetime, but you still can't use the behavior here to get the structure of the whole geometry anyway.
No, so there's two different things. There's the geometry and then there's the state. This is just a statement that the state, the quantum state, is entangled. Like the vacuum is entangled. You're only learning, so there's a bunch of stuff. We're going to review it between this class and the next one. There's a bunch of stuff about the vacuum that you can derive just by assuming translation invariance and all sorts of things in local quantum field theory. And, you know, the statement of the vacuum is that it's annihilated by all of the momentum, all of the annihilation operators at any momentum. And that tells you about locality and the geometry, because momentum ties like energy in space, you know? So you do get some information, but it's not like you're getting information about the geometry, you're just getting information about the state. And it assumes some symmetries of the geometry, maybe.
I think you've got geometry from entropy.
That's a very non-standard map. It only, yeah, that's it's a whole other story. We maybe we'll get to it in the last lecture, but not in the realm of what we're talking about today. Okay, so entanglement. So show of hands, who feels comfortable with the idea of entanglement, you think? Okay. Half of you confident, other half. Okay. So we're going to do a simple example. We're going to talk about a single spin. Single spin, I mean an object where the Hilbert space is two-dimensional. So I have a state that's called up, state that's called down, spin down. If you want, you can represent that by a 2 by 2 column vector. Okay. And there's a nice way to represent this Hilbert space. And some people draw this. You might see it in textbooks. So people draw this sphere. Up here, you have the up state. Down here, you might have the down state. Over here, you have up plus down over root 2. And over here, you have I down minus up, no, plus up over root 2. So, can anybody tell me what is the significance of these states? Yeah, or okay, these are more complicated answers than I'm looking for. Yeah. Okay, so ill-posed question. I just meant that this guy is an eigenvalue of sigma z. This guy is an eigenvalue of sigma x. And this guy is an eigenvalue of sigma y, where sigma x is 0, 1, 1, 0. Sigma y is 0 minus I, 0. And sigma z is 1, 0, 0, minus 1. Very simple. Okay. So what that means is that none of these is any different from the other, right? You have a bunch of operators that form an algebra. They act on your states. You have a two-dimensional Hilbert space, and you can choose whatever basis or whatever state you want. Like, how do you label your state? And you can choose your favorite, the sigma z basis. This is the sigma x basis, and there's the sigma y basis. Okay. So this is a very uninteresting quantum mechanics. There's only two states, and you can take linear superpositions of them, which is why you fill out this sphere. What's interesting is when you consider tensor producting this Hilbert space. So you have two spins now. Okay? So now when I have two spins, now my Hilbert space is the span of, and I'm going to work in the sigma z basis of down, 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 up, up, down, and up, up. Right? You guys all remember this? Okay. Now that we have two spins, now we can talk about entanglement. Okay? So we're gonna do a little exercise just to see who's awake and who's not. Monday morning, get your, brain muscles, warmed up. Okay, I can erase this, right? Okay. Your exercise right now, should be a quick one. So show that if I start from this state, I'm going to call it psi. And I'm going to call spin 1 x and spin 2 y, just to just distinguish between them. Okay. So show that by acting on with operators that only touch x, so for example, we have 1 tensor 1 plus sigma x tensor 1 sigma y tensor 1 sigma z tensor 1. Then you can generate all of H. So it's clear what I mean by this? That means that I only have operators that touch sigma x and acts like the identity on the sigma y guys. So chat with your neighbor, see what you get.
X and Y are labels, right? Like
Yes.
everyone in-
Yeah, exactly. So this is x, and this is y.
You're only considering the basic Fourier operator. We consider any operator.
Yeah, but that's a basis that acts on
Yeah.
up down on any 2 by 2. You can construct operators. It's a definition, not a theorem, but it's a definition of a type of state. You mean you're talking about Reschlieder? Reschlieder is a quantum field theory statement. This is not quantum field theory. This is two spins. But the analogy holds, yeah. Reschlieder? You know this? Reschlieder is the statement that if you have a quantum field theory, then your Hilbert space is dense if you act operators only in the region R. So you can get arbitrarily close to any state in the Hilbert space, any state that is continuously connected to the vacuum by acting only in a region, in a subregion. Do we believe it? It's proven. It's you can't. It's a mathematical statement. The operators that act in R are not unitary. So you can't create arbitrarily. You can't create like a Death Star like very far away because we only can act with unitary operators. I think if you're doing a quantum simulation, you can do whatever you want. But like in the real world, we can only act with unitary gates.
It's not exactly non-unitary
Sorry?
They started building non-unitary gates just to see what happens.
Yeah, I think you can do whatever if you want. If you build a quantum computer and you start like acting with states, it's just you're doing some quantum simulations. How are you guys doing on this exercise? I hear a lot of quiet. Does that mean people are done? All right, I'll give you a hint. What is the action of sigma z tensor 1 on psi?
So then we're this called X space.
No, these are labels x and y, but these are eigenstates of sigma z, right? Okay, so you got 1 over root 2 minus down, down, plus up, up. Okay, so what happens if I add this guy with this guy? You get the second term. So it's clear that if I act with 1 plus sigma z tensor 1 and over root 2 on psi, I get up, up. Right. So this is plus or minus, and then the minus also gives you down, down. Okay, you guys agree with that? So that's how you get down, down, and up, up. Okay, it's a little bit more complicated to get up, down, and down, up, but I'll tell you the answer.
But you just act with sigma x equation and then like
Close, close. Not quite. Correct. Correct. Sigma x plus I sigma y is raising. Sigma x minus I sigma y is lowering. So sigma x minus I sigma y over root 2 tensor 1 acting on psi is down, up, and plus is up, down.
yeah, but this is exactly 1 plus sigma z times sigma x. Because
Well, yeah, fine, but that's you're using the algebra, but it's the same. It's all the same. Okay, so everybody is happy. We can generate the whole Hilbert space by acting on psi locally on x, right? So that's interesting. So now here's my question. So second question. This one should be quick. Can I generate H by local operations on X by acting on the following state? Let's call this guy chi. and this guy is down x, down y. Is it possible to generate the whole Hilbert space by acting on this guy? No. Why not? Yeah, nothing you can do gets y to up. So if you act locally on x, there's no hope of ever generating the Hilbert space. Okay, so we've seen that there is one state, which I called psi, which can act locally and generate the Hilbert space. Another state, which I've called chi, no hope. Is there an invariant way to tell the difference between these states? What's the difference? This one's factorizable. What's the difference using a key word that I've been saying since the beginning of today's lecture? Yeah, exactly. The first one's entangled. The difference between these two states is entanglement. And it's the crucial thing with this Resch-Leiter theorem that allows the Resch-Leiter theorem to apply in the Minkowski vacuum. The Minkowski vacuum, as we just showed, is entangled. Okay? I know you can't see that camera. Oh, you can see it. Okay. So the difference, the important thing is that this is an entangled state. And remember, we showed that the Minkowski vacuum is entangled, right? Just go into Rindler coordinates, and you see that the Minkowski vacuum is a highly entangled state when you think about it in terms of the Rindler creation operators. Okay? If I wanted to quantify how entangled this state is, well, what I would do is there's a set of operations that I can do. To measure the amount of entanglement. So step one, I define a density matrix for rho psi, which is just the outer product of psi with its bra. You can construct this. And then you can create the reduced state on X by taking, so I call that rho X psi, which is equal to trace over Y of rho psi. And if I do this, then I have a new density matrix that's only defined on the X Hilbert space. You can do this calculation at your own time. And one thing I can do is I can compute the von Neumann entropy of rho psi X, which is minus the trace over X of rho psi X log of rho psi X. And I would get log 2. There are 2 bits of information. If I trace out Y, I still have 2 bits of information in this state. I can do the same with rho chi. So I construct rho chi, which is chi chi, this guy. And I run that machinery, and I compute the von Neumann entropy of chi just on X, which is trace the minus rho chi X log rho chi X. And that's equal to 0. So if I trace out Y in this state, I have no more bits of information. Huh? Here?
No, what are you like, over it right now?
That's log 2.
No, the x. On x.
Oh, von Neumann.
So that is the first.
Chi on x. This is the state chi. And then I've traced out y. So what are these quantities, these von Neumann entropies? They're actually called entanglement entropies. Have you guys heard this word before? An entanglement entropy tells you how much information about another system you still have once you trace it out. You have two subspaces. You trace out one. How much information about the other subspace do you still have in your state? That's what the entanglement entropy measures for you. And now on psi, if I trace out y, I still have 2 bits of information about the y Hilbert space. In chi, if I trace out the y state, I have no information left about that subspace. So this is an entangled state. The state carries information even if I have no access to y. This is not an entangled state. You can measure it quantitatively using these entanglement entropies. Okay. Another way to say another mnemonic is that state is pure and this state is mixed. Mixed state has entanglement. This pure state does not.
So because psi is pure still, but just when you go to reduce it back.
Yeah, correct. Psi, when you trace out y, rho psi on x is the mixed state. Rho psi on y, if you trace out y, you'll just get a pure state again. So when you view this entanglement entropy as a von Neumann entropy, this is what tells you that you have a pure state. Log is 0. Okay. Is that clear? All right. So entanglement is an important notion. And I'm going to spend the next maybe 10, 15 minutes or so refining these ideas of, I'm going to go through these ideas of entanglement entropy, what they really mean, because it's going to be very useful when we actually formulate the information paradox. So I'm going to try to take it slow, and I'm going to try to give you a good foundation for understanding what we're going to how we're going to phrase the information paradox. So we're gonna take a step back after this, and we're going to introduce notions from classical information theory, build that up, and then give the quantum analog, and then state the information paradox. Okay? Very good. So now we're going to introduce some notions from classical information theory. But just keep the goal in mind, okay? Don't let this digression take your mind off the prize. We're aiming for the information paradox. I just have to set everything up. There's a lot of moving parts. So remember, first lesson, black holes have temperature, and they have a negative specific heat, so they radiate. Second lecture, how do you derive that temperature from first principles? And in doing so, we showed that the state of the quantum system is entangled. Now we have to understand what entanglement means, how it carries information. All of this is in order to set up the problem. Okay? So I know there's a lot of moving parts, a lot of new concepts introduced, but just, eyes on the prize. We're going to stay in this together, and we're going to get to the end. And it's not going to be too painful, I hope. And if it is painful, then stop me and ask questions. Okay? All right, so classical information theory is very important. part of the problem, so we need to understand it a little bit better before we can phrase the information paradox. So classical information theory. Okay, so if you want to go more in depth into this, I learned a lot of these from this review by Witten. I'm sure that there are better reviews or more comprehensive one, but this one is called A Mini Introduction to Information Theory. So if you read those, you might see some overlap with what I'm about to say. Okay, so consider a string of bits So a string of bits, you know what that is. 0, bunch of ones, 0, 0, 0, 0, 1, 1, 0, 1. And it has length n. Okay. And let's say that 0 occurs with probability p. So just to see who's paying attention, what's the probability of a 1 occurring? 1 minus p is the probability of a 1. Very good. Okay, so as n goes to infinity, how many distinct messages can I have? No, but I want the behavior as n tends to infinity. All right, let's keep n finite. What is the number of distinct messages? I have n bits, and I want to choose the number of zeros or ones. The number of distinct messages. I just want the number of messages, so it doesn't matter. N choose Pn. Huh?
Oh, I get it. I get it. There are PN ones. Sorry, 1 minus P and ones and PN zeros. So the number of every message will have PN zeros and 1 minus P and ones.
So I have to pick some subset of Pn zeros. I didn't say the probability. Well, I said, what do you mean? Of a zero occurring.
Yes. Yeah. And then goes to well, and then goes to infinity, the probability becomes certain. Yeah.
Yes, but someone like take that. Yeah, but the whole number of messages is also there. Like
I have a message.
Probability of this message is not zero, so it's possible.
No. Oh, I think there's a misunderstanding. No, not zero being the message. This
Of a
this
bit
being
zero, yeah.
And then in
No, of course,
big
yes.
P and zero. The problem
Maybe I don't understand the confusion.
Well, how many distinct messages, right? So
As n tends to infinity.
yeah. Well, I mean,
No, I think the confusion is what say zero occurs with probability P. Yeah. Say zero occurs with probability P means that every message will have, on average, n times P.
yes, this is number of average.
As n tends to infinity, yeah.
That's not number of distinct.
No,
I mean, you have a large set n, a large message with n letters, and you're going to have in that message p n zeros. Because, that's because the number 0 occurs with probability p. So the number of distinct messages is you choose pn out of that number n, and then and that's it, right? I,
Even if Euler machine, I think it's something to learn about and the very
are we good? Everybody cool? We cool? Isn't it the Poisson distribution?
yeah, that is like if we
Yeah, I'm not sure. I don't have a good answer to that question. Okay, so we have n choose Pn. Everybody's cool with that now. No lingering disagreement. Maybe the phrasing you don't agree with, but you can see what I'm going with, right? Okay, very good. Okay, so let's write that down more accurately. So that's n factorial, Pn factorial, and then 1 minus P n factorial. Okay? So that's n choose Pn. And let's use Stirling's approximation, because n is large. So we're just going to take the leading part of Stirling's approximation. That's n to the n divided by Pn to the Pn times 1 minus Pn to the 1 minus Pn. Yeah? And if we do a little bit of, so approximate. If we do a little bit of manipulation, this is P to the minus Pn times 1 minus P to the minus 1 minus Pn. Which I can write as the following: e to the n times some quantity s. What is that s? Can anybody tell me what s is? That's just more explicit. Very good. So indeed, this is what we call the Shannon entropy, or Shannon, Claude Shannon. I dare you to say Shannon entropy next time. So this counts the number of messages. This tells you how much information your alphabet has. You have an alphabet. Here it has zeros and ones, and your zeros occur with probability p. So this is telling you how many things you can say in this alphabet. That's what the Shannon entropy tells you. Okay, so if I have an alphabet with k letters, so if I have an alphabet with k letters, Then, and each one occurs with probability pi, then my S is just going to be minus pi log pi, and then summed over I. You've seen this expression before for the Shannon entropy. Okay, so it's just a little reminder of what this is. Can anybody tell me, for an alphabet with K letters, what is the maximum possible Shannon entropy? Very good. Pi is 1 over K. That's the maximum amount of Shannon entropy you can have. That's the most, you can encode the most number of messages in your alphabet if all of the letters occur at equal probability. So S max is minus 1 over K, sum from I equals 1 to K, 1 over K log 1 over K, which is just log K. Okay? So that's what the Shannon entropy is. It's a count of information. It's a measure of information. How much information is captured in your system. Okay? Now remember, we started this entire lesson by talking about entanglement. So when you have a partition of your Hilbert space, right? You can put some of your information in half and another part of your information in the other half. Right? So now we want to introduce a measure of entanglement or of information that that considers the split. Okay? So now let's remind you what is conditional probability. Okay, so I have two random variables. Like before, I'm going to call them x and y. And x, think about it as like, a state vector, x1 to xn, and y is like another state vector, y1 to yn. All of this is abstract, but you can think about it as like a bipartition of your of the information that you're interested in. Okay, and I have a joint probability distribution. Which I call PXY. So this is just a distribution on the state of both x and y, right? This is just describes the state of my system. If you want to think about the bits, I have two bit strings, and each one has probability of a certain string occurring, and this is what the joint probability distribution is. Okay, and I can define probabilities on x and y as the sum over the state y. Yeah, so this is, let's say this is P of x is set xj, which is the sum over y of P of xi, y, sum over j, yj. this should be an I. So it's clear when I write something like this, and this is Pxy. So I define the probability on X by summing over all of the states of Y, all of the possible states of the string Y. And similarly, I have a probability distribution just on Y, which I can get by summing over J, and this is on Y of P of X Y X J Y I. So I define my probabilities, so I have a joint probability distribution on both X and Y, and I can integrate over Y or integrate over X and produce for myself a probability distribution on just X or just Y. Standard thing that you do in probability. When you have a probability distribution, you can integrate over something that you're not interested in and generate a probability distribution on the degrees of freedom that you do care about. Okay? So once I have that, I can define a couple of useful things. And then, I don't know, is it break time, Sasha? Yeah, I'll define this last thing and then give you a 5-minute break. Okay. We can define a conditional probability. So the conditional probability, we say P of X given Y. And so that's, we write it like this. And it's equal to P of X Y Xi Yj divided by P Y Yj. So it's, and this is the probability of seeing, of observing the string X given that the state of Y is this state. That's this condition, this notion of conditional probability. Okay? So it just follows from this definition when we have two sets of variables we're interested in, and we can define subprobabilities, then we can define conditional probabilities. It's the joint probability distribution divided by just the probability of that state Y. Yeah? Yeah. I mean, you can think of Xi as whatever you want. So here, we're being very general. It's just some system defined by a state. We're going to represent it as a state vector, but it's state vector on all of X. Okay? And last thing before the break is that given you have a conditional probability, you can define a conditional entropy. Which is, we write S of X given Y equals this state Yj, and that's just the Shannon entropy. Okay? These are just definitions that we're going to use after your break. So, just a reminder. It's important to, like, eyes on the prize. I'm not just defining these things because I like defining things. It's not the best. use of your time. So we worked out that we have an entangled state. The entanglement is between two sides, left and right. So now we're trying to build up the notions of how to quantify or measure entanglement and like how much information is carried if you only have access to one side of the system, right? So black hole information paradox is all about, you're standing outside of a black hole. Black hole somehow has an entropy. What does that mean? How do we quantify these? Is the sound working, by the way? Yeah. How do we quantify how much information we have access to when we're standing outside? We don't have access to inside. So that's why we're going through this whole digression on joint probability, mutual conditional probability, conditional entropy. Okay, so we have this conditional entropy. Remember, the entropy is a count of the number of distinct statements, like how much information, right? So a conditional entropy is a statement of how much information is in your system X, given that you measured a particular state Y. That's what we are building up to. Okay, now if I wanted to know the entire entropy in X, if I only had access to X, how do I calculate that? Well, I take the probability on Y of my state Yj, and I multiply by conditional probability X, Y equals Yj, and then I sum over all of the possible states Yj. So if I sum over Y, let's do that out. Okay, so let's do that explicitly. I'm going to use my handy dandy formula over there. So this is the sum over the Yj's, Py of Yj, sum over yeah, sorry, this should have been a sum over X, right? Because it's an entropy. Trace of rho log rho, sum over the state. So then sum over xi of p, the joint probability, p of xy, of xi yj, divided by p yj, py, and then log of that quantity. Just use the definition, right? Okay, so we can stare at this a little bit, and we'll notice something. We can rewrite it like this: sum over xi and yj of p of xy log p of xy plus the sum over xi and yj of p of xy log of py. And here, if I sum over x, I'll get py, right? So I'll get py log py. So what is this? And this should be a minus over here. Well, that's the total entropy over x and y minus the entropy in y. And we call this the conditional entropy. So this tells you the conditional entropy of that's carried in x, given that you measured y. Right? Given that you measured y, this is how much entropy that you'll have in x. So the total entropy minus the entropy in y. Okay? So remember, it was the sorry, did I call both things the content? Yeah, I didn't. I don't want to. This is the conditional entropy of x given we measured y.
Given that we're saying we measured y, why are we still starting over y?
It's just a question of how much entropy is in the x subsystem once you're no longer once you have fixed the information in y, right? Like you fixed one state in y.
But then why are we still starting over saying y?
But the amount of entropy, is a question of how much information can be carried in the whole subsystem of y. It's is that a good answer? We've measured y. Somebody else measures y and you don't know. You're still in this state of you don't know anything about y. Okay. So this conditional entropy of x given y is the amount of information remaining in x once y is known, right? That's what this measures for you. So you just take the total amount of information and you subtract out the information in y. So it's the total amount of information left in the system x, in the subsystem x. Okay? So the last thing I'm going to introduce for you is something called the mutual information. Good? Okay. So the last thing I'm going to introduce to you is called the mutual information. So the mutual information is I'm going to write it x, y, and it's defined as Sx minus S, the conditional entropy. And I should have written that I call this guy Sx. So this, if we just write this down, Sx plus Sy minus Sxy. So the mutual information is it's a symmetric quantity, as you can see, between x and y, and it tells you like since it's symmetric, either x or, this applies to either x or y, but it tells you about the amount of information that you learn about one system, given that you've measured the other. It's a symmetrically defined object that, as you can see, this conditional entropy tells you how much information you measured in X, given or left in the state X, given that you measured the state Y. This mutual information symmetrizes it and tells you how much you learn about one system given that you know the state of the other. Okay? And the nice thing about the mutual information is that it is greater than 0 by definition. So, well, you just have to go back and plug this in, plug this definition in, and you'll see that it has to be greater than 0. SXY minus SY, it should be greater than 0, I think. SXY has to be bigger than SY. Okay. So, we've defined a bunch of notions from probability theory and information theory. All these things are trying to tell you is, say that if you have two systems, you know roughly about both systems, some probabilities about being in one state or another. And the question is, say you now learn some information about one state, but you're ignorant about the other, or vice versa, how much information do you get? All of these quantities that I've defined here quantify that, the amount of information that you get when you look at one subsystem or another, given that you know a little bit about each one. Okay? And the important thing is that, of course, I've defined all of these things for classical probabilities, but all of these definitions can be generalized in quantum, for quantum states. So instead of just classical probabilities here, you can define density matrices and replace these probability distributions with traces over subsystems, just like we did in the 2-spin example earlier, right? We defined the entanglement entropy, which was like conditional entropy, given that you have, how much information is left in one system once you've learned about the state of the other, stuff like that. Okay, so again, we define our entropies. Instead of Shannon entropies, you use von Neumann entropies, trace rho log rho, but all of these definitions hold. Okay? Okay, so let's bring it full circle. So remember, we started by introducing two states. One state I called chi, which was up. Was it up, up? No, it was down, down. Down x, down y. And I introduced this state psi, which was down x, down y, plus up, up, x, y, over root 2. And you can go home and do the following calculation. The mutual information between x and y in psi is 2 log 2. It's twice the entanglement entropy because it's symmetric. And the well, I called x the one spin and y the other spin. So any guesses? Big fat 0. So there's a nice theorem that I'm not going to prove, but you can show that, you can show that if the mutual information between x and y equals 0, that happens if and only if rho can be written as rho x tensor rho y. And then I'm going to make one last statement about information theory, and then we're going to phrase the information paradox, because we'll have everything that we need to make the statement. And I'm going to keep these on the board. Okay? We're not going to erase them. So the mutual information is 0. I have a state that's a tensor product. And I'm going to write. So we already saw, I'm gonna write this, so I of xy, xx plus sy minus sxy is greater than or equal to 0. So that's one inequality. So that's one. Two is something called the Araki-Lieb inequality. And that says that Sx minus Sy absolute value has to be less than or equal to Sxy. And finally, there is another one that's proven. It's called strong subadditivity. And I know you guys can't see this, but strong subadditivity imagines now I have 3 subsystems rather than 2. And it says that the mutual entropy on all 3, Sxyz plus Sy, is less than or equal to Sxy plus Syz. It's Sx minus Sy absolute value is less than Sxy. So we can phrase this in terms of mutual information. It says that the mutual information in x and y over x and y is less than the mutual information if I include z with y. That makes sense, right? If I have, so the mutual information tells you how much information you learn about x by measuring y. Well, I learn more information about x by measuring y and z than I learned just about x. And that's because x could also be entangled with z. Okay? So we want to keep these in mind for later.
Is my xyz xyz minus y plus n minus z, or sorry, is it
Just replace y here with yz.
oh y times z?
Yeah, y, and it's like the inclusion of the state of y with the state of z. It's like the joint probability of y and z. Okay. So now we've done a whole reminder of information theory. We understand the problem is all about quantifying information in one space versus another. And now we're going to try to set up the information paradox. Okay? I have almost 30 minutes to do this. Not quite, but we're going to do it. Okay? Is that clear what we're going to do now? So I want you to remember that these guys I didn't just introduce them for shits and giggles, like we're going to use them. Okay, so sometimes we call the information paradox a crisis of entanglement. So, the BHIP. The BHIP, at the end of the day, is a problem with basic notions of information theory and the time evolution of a black hole. And in order to make that precise, we really need to show where the bodies are buried. If you don't show where the bodies are buried, then people will doubt that there's a problem to begin with. You might have been, hiding stuff, pulling a fast one. So we need to really specify what the problem is. Okay. So imagine we have a black hole formed by a collapse of a star. Because if you don't have such a thing, there's not really a paradox. So black hole formed from collapse has a Penrose diagram that looks like this. Say there's some pulse that falls in and forms a black hole. And now remember that I'm an observer outside of this black hole. Right? So we're considering observers who live outside of the black hole. And the observer is a person who has the tools of weakly coupled quantum field theory at their disposal, and they're observing the evolution of this state, right? Okay, and now remember that we usually quantize. So in order to use quantum field theory, we quantize on complete Cauchy slices. So there it goes.
Is that vertical, or I thought if it was, if we're talking about the Cauchy place before the thing between the black hole, wouldn't that be
What? Which one? What?
the infinity on the left wall? What kind of infinity is that? That vertical?
This one? This is space-like? This guy?
Yes.
This is the origin. There's nothing there. Yeah. So the origin, at some point, you hit a singularity. Okay. So I need to tell you a little bit about the slices on which we're going to define the QFT Hilbert space. So a little bit about slices. So to formulate the problem, we need to be in the realm of weakly coupled low energy effective field theory. Everybody knows what I mean when I say that? Well, it has to be dynamical because we can form a black hole, but we want to. Yeah. So we're going to assume that there is some QFT Hilbert space that includes the graviton. It's weakly coupled, but of course that's a very difficult thing to make precise. But the the basic assumption is that that's a good approximation when curvatures are low and when energies are low. Okay, so we need to make sure that we're always within that regime, always, right? No, we're taking the metric to be the metric of a black hole that forms from collapse. Okay. Okay, and remember, we quantize on Cauchy slices. So I need to tell you what Cauchy slices I'm going to take. Okay. So so first of all, I'm going to tell you that I need my, okay, so I'm going to work in 4 dimensions, just like the space-time we were in. Okay, and my space-like slices, my space-like Cauchy slices, need to have intrinsic curvature, which is much, much lower than the Planck scale. So it's a 3 curvature because this is a slice. And there has to be no place in this Cauchy slice where I bunch up a bunch of curvature. Because if I do, then I'm outside of the realm of weakly coupled, weakly curved EFT. Okay. And I also need the extrinsic curvature. So extrinsic curvature also needs to satisfy that. So we call that K also has to be much, much less than the Planck scale. Also, I'm considering the evolution of slices, right? So at the same time, the 4 curvature in the neighborhood, so the so the 4 curvature in the neighborhood of any of the slices must be also much, much less than the Planck scale. So those are the statements about the curvature. I want to keep these up. So let me know once you've copied this, and I'll erase and continue. You guys have copied? Okay, so now condition 4 is about the quantum state. So the quantum state on my slice should be low energy. So that means that no modes with wavelength lambda much, much less. So the modes should be very big compared to the Planck length. So modes are always much, much greater than the Planck length. Very low energy modes compared to the Planck length. And the energy momentum densities must also be small everywhere. Okay, so all of these are conditions so that we're always in the low energy EFT. We're going to quantize on a certain set of slices that satisfy these conditions, and then I also am going to need to take the state on my slices to always be low energy. So the entire statement of the Cauchy of the information paradox is a statement that you set up a problem in low energy EFT and you derive a contradiction. Okay, set up a problem in the low energy EFT and we derive a statement that can't be true. Very good. So the good thing about it is that we can choose our Cauchy slices. And I'm going to construct the Cauchy slice for you. Okay? So how do we make such a slice? That's the question. How do we make such a slice? So I should mention a reference. I learned all of this stuff from a nice review by Samir Mathur, and it's in the suggested reading. Okay, so how do we construct such slices, right? So remember that we wanna make sure that we're always in the weakly curved region. So we have to stay away from the singularity. If we get close to the singularity, then the three curvatures will blow up or at least violate our assumptions, and the four curvature will also violate our assumptions. Okay, so let's construct these slices. So this is a constructive definition of these slices. Can I erase this? Okay, so for R, so outside of the black hole, we're going to take this static approximation, which is good for short time intervals. The metric is the one that you know and love. And remember, the black hole horizon is at R is equal to 2m, right? So outside of the black hole, we're going to take this to be our metric. And for R greater than 4m, we're going to take t equals constant slice. So for R greater than 4m, this is this part of the slice. T is equal to constant. Extrinsic curvature is small. Extrinsic curvature is small. So that's a good it's a good part of the slice. Okay. Now, for R less than 2m, we're going to take R equals constant. So R is equal to constant is space-like for R less than 2m. And so T is in particular not constant. So, and in particular, we're going to choose R, this constant. So I'm going to define R1. We're going to take R1 to be less than 3m over 2 and greater than m over 2. Okay? So, so that we're always away from the singularity. Okay. So I've told you large R behavior and small r behavior. And now I need to tell you how I connect these. And so I connect via a smooth connector. So what that means is that I always make sure that I connect my R constant slice to my my T constant slice by something that is a smooth function that has nowhere derivatives such that I can excite modes that are high energy with respect to the Planck length. Okay. And I'm going to draw these slices for you. So here is the horizon, and then this is so this is R equals 2m. This is, where's my yellow chalk? This is R is 4m. So here is my R is equal to constant part. And here is my T equals to constant part. And then I have a connector region that's always smooth, no derivatives, are big. And a later slice will look like this. T constant, and then it goes to the same R, and then connect. Yeah, for R less than 2m, we're always going. Okay, and these are the connectors. So as time moves forward, slice 1 evolves into slice 2 evolves into slice 3. Okay? Okay, now, setup of the problem. You remember that we're an observer outside. The observer outside is going to observe a thermal bath. We derived that, right? That was the exercise of the last class, right? It's the equivalence principle. This is you have to stay at you have to stay at constant acceleration to not fall into the black hole, and therefore you're like a Rindler observer, staying outside the black hole. You have a particular temperature, and it doesn't matter what coordinates you choose. You're going to find the same answer if you've done the calculation correctly. Okay. So now we're going to work in these coordinates. These coordinates, everything looks slightly different, but the Penrose diagram is very similar to the Rindler problem, and the physical implications are the same. Still measure a thermal spectrum. But now you can kind of see in these slices where that thermal excitation is coming from. So the thermal excitation is coming from the connector. The connector is the only place in the Cauchy slice that has any curvature that's going to stretch as you move from this Cauchy slice to this Cauchy slice. And the stretch of this connector into this connector is what, in these slices, and again, this is just a statement about these slices, will generate the particles, the excited particles.
So when you purchase license, you need all of the connectors to be stationary, right? For the rent. And so is it that as you approach the where they start getting relatively boundless, that the likelihood is that they shrink smaller and smaller? I don't know if that makes sense.
The light cones shrink?
In the sense that if the light cones get thinner vertically, then it leaves more space for the red curves to turn vertical. I don't know if that's the word.
I'm not sure I have a good answer for you right now.
Maybe my question, a better question would be, are the red lines space-like in this space-time?
Yeah, they're supposed to be. Yeah, everything is space-like. Yeah.
Right, even as it like starts going red.
I mean, this is a space-like slice, so it's just.
And sometimes going up is in the background, right?
Yep, but it depends. It depends on where time goes up here.
Yeah, in this chart.
In that part, and here this is space-like, so time goes this way.
So the light cones, the left go. What are the light cones that like?
Well, they tip over.
Right, that's what I mean. So,
At the horizon, there's everything else.
Well, the generator of the horizon is null, so the light cone would be tangent to the horizon. But then they keep tipping.
How would you go about on the tender diagram? What was the origin constant line always tended to that time like infinity? Future time like infinity.
I think on this it would just, I mean, it kind of looks like this. I don't know how that is.
Like, the origin constant not in the future time like infinity.
Are you asking if it hits the singularity?
Not the singularity, the future time like the point of the singularity.
This part.
No, the other side. Where you get that.
This?
Yeah, the origin constant always get that.
Well, no, this would always be in the connector. This would be in the connector. This is a very far future. This diagram degenerates here, so you don't really see what's going on here very well. Yeah, the connector is what connects outside of the horizon into inside of the horizon. Anyway, at very late times, this is a bad diagram for the black hole because the black hole evaporates. Okay, so I'm not doing very well on time, but that's okay. You give me like I'm the boss. You guys okay with waiting 10 minutes for pizza?
Speaking of which, I just got a text from contact that somebody should go there to collect it now if possible. Someone that's closer to the door.
Can
It's actually downstairs right now.
Can somebody go pick up the pizza? I can wait for you.
I think I just told the pizza press is away.
Yeah, I think she has the flu.
And the code is 18 now. 1 8.
Thank you. I'll wait for you.
No.
No worries. I should continue.
Just downstairs. Just straight up.
And then I didn't get the.
I know I'm probably going to get ahead of everything. As the black hole evaporates,
Sorry. I forgot to say one thing. Very good. Sorry. I forgot to say one thing. One last thing about these slices. So, we stay on this space-like slice until we reach a point where we get to before the black hole was formed, and then we connect to r equals 0. So the slice will look like this. So follow D is follow r equals constant until before black hole collapse. Then connect to equals 0.
For r less than 2m, r equals constant, should it not be like r less than like 2m minus epsilon?
Well, we're taking r.
Because
We're going to take this constant to be well away from the. This is at like 3 halves m. That's the constant. This r1. It's possible, yeah. It's possible. You have to believe me. Okay. So now we have our Cauchy slices. Cauchy slices are all weakly curved, and they're all essentially curveless, except for in the connector region. Connector region in these slices is the only thing that produces any energy. Right? It's the stretching on the connector. You look puzzled. Okay. And we learned that the state on our Cauchy slice is going to be entangled between inside and outside. Right? So, very good. You didn't miss anything.
No.
Huh?
Yeah.
No, I know, but you didn't miss anything of the lecture.
Okay.
So, what happens? So, as you evolve from slice to slice, you're going to start populating the state outside thermally. And we saw the form of this state. So you're going to start producing pairs. And we're going to call the intrinsic scale of the slice, I'm going to call it lambda. It's kind of the amount of stretching. Okay? And the way that it works is that you're going to start exciting pairs at that characteristic scale, lambda. So the state that you're going to be in will look like a left energy lambda dagger, a right energy lambda dagger, acting on a left tensor O right. Right, this is what we derived in the Rindler case, right? That we had a, thermally populated state. It was correlated left and right, and here you're generating this thermal population, right? So at short times, you can expand this out. This will be an entangled state. Right, plus. So you clearly see that you're in a mixed state, right? You're in an entangled state, the vacuum plus one particle. Of course, this is an exponential, so you're going to generate a whole bunch of other stuff. But the state that you generate here is, of this flavor, right? It's an entangled state between the slice here and whatever's inside. Okay? And we just measured that, we just defined that you can have a measure of how much information you get outside if you ignore the inside, right? You measure the state of outside, how much information do you have about the inside, right? So if I use this as an approximation, how much information by measuring the state of the outside do I get about of the inside? What is the entanglement entropy? Log 2, right? So you imagine this time evolution. You start in the vacuum, the black hole forms. Then you get one state that is an entangled state between inside and outside. You get log 2 of entropy. You then continue this process. You generate more states. You get 2 log 2. If you follow this n times, you get n log 2. So as you evolve in time, the state outside gets more and more entanglement entropy, becomes more and more entangled with the state inside. Okay? That's what happens as time evolves. Okay? So if I plot that, that's my eraser. So if I plot that process as a function of the time, the asymptotic time on the Cauchy slice, I have S nt t as a function of t, I get this straight line. Right? But that's very strange because, okay, in the first lecture we derived that the black hole is a thermal object, has a negative specific heat, and that means that as it evolves, it wants to decay, right? So as this thermal spectrum gets more and more populated, actually the black hole shrinks in flat space. And if I look at the black hole entropy as a function of time, it'll look like this. This is the black hole entropy. This is the entanglement entropy. So let me. This is S. This is S black hole. This is S entanglement. And the calculation from effective field theory tells you that the entanglement keeps growing. We're using nice slices, so effective field theory should be valid. Nevertheless, the entropy of the black hole keeps shrinking. And at some point, you only have the radiation outside, no black hole anymore. And the radiation outside isn't entangled with anything because there's no inside. So this calculation has to give you something wrong. So the first idea was that actually if you could do something correct, the curve for the entanglement outside you should get would follow the red curve. And this thing is called the page curve. And the trouble is that it's impossible to derive the page curve within low energy effective field theory. Even though I'm always working in nice slices, there is the low energy effective field theory always gives me this answer, even though the black hole is shrinking and there's less and less for me to be entangled with. There's a final way to make the statement that uses these quantities. I'm going to end with that. I'm really apologizing for being so over time. But let's again draw our black hole. And actually, I'm going to draw the quantum corrected Penrose diagram. So the way people draw it is like this. You have a black hole formed from collapse and then evaporates, and then you're back in flat space. That's what this Penrose diagram looks like. And let's work on some nice slice. And the statement is that we're very close to the end, and we're working in this region of the page curve, right? Like the entanglement entropy should be going down, right? Say that we could derive the page curve. Okay, so the final Hawking quanta that's released by this black hole will be, I'm going to call it a quantum, this Hawking quantum, I'm going to call it B, okay? The final Hawking quantum. And then the rest of my state will be some bath of radiation. I'm going to draw that here. The radiation is far away from the black hole. I've been collecting it in my lab for a long time outside of the black hole. And I'm in this part of the page curve. I'm at the very end. So that tells me that if I've done calculations correctly, then the entropy of my state, rho b plus the radiation, should be very close to 0. Right? Now, let's use the inequalities that we derived before. Okay? Or that we defined before. I'm going to use the mutual information is greater than 0 and the Araki-Lieb inequality. Okay? I'm going to use these two to show something that's bizarre. Okay? So I'm going to use these two, and I'm going to call x. X will now be the interior. X will be the interior quantum. And y will be b plus radiation. Okay? So x will be the stuff inside this very late black hole, and y will be the stuff outside. Right? It's my old radiation that I collected plus this new Hawking quantum. So let me use my mutual information. So this is Sx plus Sb plus R minus Sx and B plus R. And that's greater than 0, right? By my original statement. And this guy is 0. So I have Sx is greater than the total entropy of the inside plus the outside. And now let's use Araki-Lieb. I have Sx minus Sb plus R is less than Sx B plus R. And this is 0. So what have I shown? Here I've shown that it's bigger, and here I've shown that it's smaller. So it has to be this is less than or equal. Equal. So we've shown that yeah. Okay. So now, if I plug this back in to my mutual information, what do I find? So I've just shown now, because I've proven this, that my mutual information is 0. What does that mean? The state of the inside and the outside is a tensor product, which is a contradiction. We derived initially that the state was entangled in order to make all of these calculations. Low energy effective field theory in this background says that I have an entangled state between the inside and the outside. If I want to solve the problem and get a page curve that goes down, I have to go away. I have to be able to show that at some point the state becomes factorized between the inside and the outside. Factorized between the inside and the outside is not within the realm of low energy effective theory. So, where did I make a mistake?
also saying that the black hole is operating?
The answer we don't know.
Well, but like the 2m is still decreasing, so eventually the closest cycle is still going to hit singularity.
Is the answer all of the above are possibilities? Yes, I know.
No one knows where the mistake is. Nobody can find. The problem is that you can try to be as careful as you want, and something doesn't fit. You, these nice slices are designed to keep you within the realm of low energy EFT, and those will always predict that you're in an entangled state. So there's no way, so either these nice slices don't exist, there's no way to stay within the nice slices, or if they do exist, which everybody hopes is true, then maybe space-time doesn't make sense, something violent happens to the geometry. The answer is actually no one knows. And next time we'll talk about some possible resolutions.